down with me, Naomi.
You're welcome.
In your 2007 paper, The Scientific Consensus on Climate Change, How We Know What We Know, you discuss topics in general philosophy of science that might shed light on how climate science works. The topics you discuss include enumerative induction, the hypothetico-deductive method, inference to the best explanation, falsificationism, and consilience. Do you think some of the literature in philosophy of science can illuminate the way climate science works, and how would you describe the epistemology of climate science?
Okay, two questions. So first one first. I definitely think philosophy of science can be useful, and that, in a sense, is what I was trying to do in that paper. And subtext was to encourage more philosophers to get involved in this issue because it's such an important one. It's so interesting intellectually, and it has a lot of rich intellectual and epistemological territory. So it's both important and interesting, and that's a nice thing for an academic to find. So definitely, and so the paper in a way was motivated by the fact that I had spent a lot of time looking at people who were trying to debunk climate science and really trying to point out that that debunking was not coming from a principled epistemological stance, but was really motivated by political considerations and what I would call implicatory denial, that people don't like what the implications of climate science mean for our way of life and our political system, our economic system, and therefore rather than accept those implications, they want to reject the science. But having said that, I wanted to step back from that and said, but okay, but what if it were principled? Maybe some of these people are principled, even though the ones I studied, I would argue, weren't really. But you know, there could be a principled skeptic out there, and that principled objection merits a reasonable intellectual response. And so that's why I sort of posed this question, okay, well, how do we know we're not wrong? If all these scientists telling us all this stuff, but you know, how do we judge it? How would an informed and intelligent person reasonably judge these data if he or she wanted to? And also interested in the question that Philip Kitcher is pursuing now. In a democracy, citizens ought to ask questions about science. We shouldn't be just taking it on faith. And yet, if we're not climate scientists ourselves, on some level, you know, there's a point at which we do have to rely on experts. So what can we do to judge this expert knowledge? And the answer I came up with, well, really, philosophy of science is probably the best tool we have, because that's the domain of expertise. That's where we have expert knowledge about the question about how we judge experts, or how we judge expert knowledge. I mean, obviously, sociologists of science have something to say too, but it's a different something to say. So I just drew on my own training in philosophy of science to say, well, look, if we wanted to judge knowledge, if we wanted to say, we have this body of knowledge, scientists are telling us these are true things about the natural world, how do we judge it? And one of the things that I've found in my years of teaching and lecturing is that many scientists are very opinionated about what constitutes good science, and many scientists will tell you that the scientific method is X. But anyone who's studied the history and philosophy of science knows it's more complicated than that. And we know two things. We know from history that what scientists have thought was the scientific method has actually changed over time. What scientists do to do science has changed. And what philosophers have thought they should do has also changed. And philosophers have argued at great length about what good science should look like, or what constitutes the scientific method. And I would say one of the big advances in history and philosophy of science in the last 30 years, particularly on the philosophy side, is that philosophers have now also recognized that there isn't really one method that explains everything that people in science do. So that's good. That's kind of opens up a space to think about different methods. And so what I tried to do in the paper was not to say, okay, is this scientific in the sense, does it follow the scientific method? Because that would be a meaningless question, but to say, okay, let's look at a range of things that philosophers have said are candidates for scientific method, or are candidates for judging the reliability of scientific knowledge, and let's subject climate science to all of them. And then nobody can argue that it's cherry picking or special pleading, because if I like a particular model of science, like I like inductive science, I could say, oh, but look at all these data, you know, this gigantic induction from all these data, but that could be viewed as cherry picking, because I'm cherry picking the philosophy. So I thought, okay, I won't cherry pick. I won't even say what model of philosophy, you know, what philosophical model I like best, because it's not relevant. I'll say, let's just take all these models and let's say, if you apply that model to climate science, does it pass that test? And what I argue in the paper is, actually answers yes to almost all of it. And there's one or two potentially little soft spots having to do with climate models, which is a long-standing interest of both of us. But I think that soft spot can be understood and explained in context. But overall, what the argument of the paper is that you have a lot of different kinds of science. They fit different pictures and different models of what science ought to look like. So whichever model you prefer, whatever test you want to apply, you actually find that climate science can pass all of those tests. And that seems like a pretty robust argument to offer to the principled skeptic.
Fair enough. You have another paper that also deals with scientific methodology. This one is from 2004, entitled Science and Public Policy, What's Proof Got to Do with It? And in this paper you state that scientific knowledge is the intellectual and social consensus of affiliated experts based on the weight of available empirical evidence and evaluated according to accepted methodologies. So on your view, scientific knowledge is characterized by these three features: methods of evaluation, empirical evidence, and consensus among experts. Could you talk a little bit about how these three features of scientific knowledge interplay in scientific practice?
Yeah, that's a good question. One could probably write a whole encyclopedia in response to that. So, thank you for bringing up that sentence, because I worked hard on it. Because in a way, this is part of the challenge. I see this as part of the challenge of post-Kuhnian science studies, or history and philosophy of science, whatever you want to call it. That we had these earlier models of science, you know, there was the whole heyday of logical empiricism, and a kind of aspiration that we could define what good scientific method looked like, and therefore we could judge science by whether or not it followed that method, and we could also use it as a demarcation criterion. And we could say this is good and this is bad, this is sense, this is nonsense, and that's of course what the logical empiricists tried to do. And that project collapsed in a great big heap, right? Although, you know, there's still logical empiricists out there, God bless them, right? But, you know, we now know that that's just, it's empirically inadequate is, I think, the most generous thing to say about logical empiricism. It fails its own, it fails actually its own standard of, you know, being affirmed by observational evidence. But in any event, so what do we replace that with? Well, Kuhn comes along and Kuhn says, look, you know, we've spent all this time talking about individuals. We talk about Einstein and Darwin and Copernicus, and we focus all this attention on these great heroes of science, but that's not how science really works. If you actually look at how science works, what scientists are doing, what you see is really communities, communities of practice, communities in which people have a shared set of assumptions and a kind of agreement on what kinds of questions they're going to address. So some questions are ruled out as not relevant, or not part of the discipline, or not appropriate, or not science, not scientific questions. So there's agreement about what kinds of questions get asked, and there's also agreement about what kinds of answers constitute acceptable or appropriate answers, right? So the most obvious example is obviously we don't invoke acts of God to explain natural phenomena. I mean, that's a kind of basic agreement, but there's lots more subtle ones as well. And so Kuhn painted this picture, which a lot of scientists really liked because it resonated with their own experience of scientific practice, and also because he made the argument that most of the time scientists are not trying to falsify their theories, so slap in the face to Karl Popper. Actually, most of the time scientists are assuming that their theories are correct and just working out the details, and that's his famous model of normal science. So that's great, and Kuhn was wildly influential, and Structure of Scientific Revolutions is one of the most widely cited books of the 20th century. But it still left us with a big problem, and in a way it was the problem of truth, the problem of knowing whether or not these agreements were right or wrong, and the problem of recognizing from history that in the past scientists have sometimes had consensus over issues that we would now say were incorrect or wrong, or at best we'd say they were partial, and at worst we would say that they were just completely incorrect, right? The Earth is not the center of the universe, right? So how do we make sense of that, and where does that leave us? And Kuhn opens up this great big space for disbelief in science, which some people run with, and some people say, see, there's no reason why we should believe science more than anything else. The authority of science is a straw man. But other people say, well hold on, okay, just because he's given us a different picture doesn't mean we have to throw out the baby with the bath. What is the basis for belief in the results of scientific work, given that we're now thinking of it in terms of community structure? And that's a really, really hard question. And I think that's, in a sense, been the $64,000 question of science studies ever since Kuhn. And I don't think we've really fully answered it. But I think we have some parts of the answer, right? And I think one part of the answer is essentially about social epistemology. That when lots of smart people work on a problem, and especially when they have a culture of not acceding to appeal to authority, but actually having to make the argument with evidence, that can be robust in the sense of strength in numbers, right? That if you bring lots and lots of smart people to work on a project, then you have more brain power, more horsepower working on it than if you just have, Descartes sitting alone in his room, right? And that's a good thing. So the community structure of science is actually part of its strength. But it's not just the community structure, because of course you could have 1,000 acolytes of a religious guru who are all saying, we are all individuals, right? And that wouldn't necessarily be a good basis for knowledge. So it's got to be something more than that. And so then there's this idea of evidence, right? And this question of data. And this is huge, right? And we can't answer this here in the next 5 minutes. But obviously it's not just about people making arguments. It's about people making arguments based on data. So there's a kind of engagement with the natural world. And to me, that engagement is crucial, because I think we can see so many good examples in the history of science where scientists thought they had solved a problem, they thought they had worked things out, but then through the engagement with the natural world, they see things that they either didn't expect or didn't predict, or maybe they predicted it but it came out somehow differently than they expected, or things that just don't add up, pieces that don't fit with other pieces. And it's that engagement with the natural world that I think prevents science from moving into the kind of lockdown that some philosophers thought Kuhn was advocating, right? Because that was one of the criticisms of Kuhn, right? That it's kind of, now we have a paradigm and we're locked into it and it becomes dogmatic and it's not science. I mean, Popper said that, right? This isn't even science, right? So scientists aren't locked down because of this continued engagement with the natural world. So obviously the evidence, the data, the observation, the experiments, crucial, right? And then the third part of the practices. And that's in a way I think the hardest part to actually get at, because it gets us back to this question of scientific method. So what are the practices? I mean, not any kind of observation counts in science, right? Certain kinds of observations described and documented in certain kinds of ways. And that's a really, really big question about why certain kinds of practices and observations count and other kinds don't. And that's something I think we have a lot more work to do on.
Do you have any starting points as to what the sort of standards of observations and evidence should be to confirm or disconfirm hypotheses in climate science?
Well, I'm a historian in the end, even though I have philosophical training. Maybe this is why in the end I got a job as a historian, not a philosopher, because the should piece is always problematic for a historian, because in a way we would have to say that scientists work that out for themselves through the process of doing science, and they come to conclusions about what kinds of observations they think are effective, and that's changed over time. But I guess in a general way we could say that clearly reproducibility is important. Certain kinds of observations that are too personal, too subjective, too individualistic don't meet that criteria for community consensus because they are too personal. So there's got to be some component of it that can be intersubjective, right? That's clearly important. Quantification is good. I don't think it's a be-all, end-all. I think a lot of people have exaggerated the role of quantification in science. But clearly, if you can quantify things, that's nice because it helps the intersubjectivity. So I see quantification as kind of a subset of the goal of intersubjectivity. And then, it has to be representable in some form, right? This is, in a way, gets to the idea that Simon Schaffer has emphasized about witnessing and virtual witnessing in science, right? So why should I believe data that you collected? Well, I could believe it because I like you, I think you're a good person, and I could believe it because you have a good track record, you've done good work in the past, and those factors do play a role in science, we know they do. Steve Chapin has emphasized that in his work. But it can't be just that, otherwise we're back to appeal to authority, right? So why should I believe the things that you claim you saw? Well, one of the things that you can do is you can get me to see it too. So scientists like forms of observation that can be seen by other people. So an experiment that can be replicated by others, or that other people can be brought into in some way, is good. So the famous example that Shapen and Schaffer wrote about was the air pump, right? Where the air pump was actually brought into the Royal Society so that other scientists could see them create a vacuum and kill the bird in it, right? You know? And if it's vivid, that's even better, right? So the bird dies and we all think, wow, that's pretty impressive, you know? And that bird is definitely dead, right? But that's not very practical and realistic in the modern era either. So that brings them to this idea of virtual witnessing, that scientists have techniques and technologies to make it seem as if we are observing it too. And that could be as simple as a photograph, right? So you can't go with me to a certain place, but you can see the picture of it. It could be an illustration. 19th century science, 18th and 19th century illustrations play a gigantic role. It could be a webcam, you know, in the modern era. Or it could be some kind of graphical representation of the data, so that even though you don't actually see the thing itself, you see the summary of it and you're persuaded that that's kind of a good enough approximation. And I think some model output plays that role, like when people make model output that then they put into visualizable forms, like some of these models now where you can see the Earth warming over time, or you can see hurricanes forming over the Atlantic, you know, the Gulf of Mexico. Those kinds of visual outputs are really nice, right? Because we feel as if we're seeing the thing, the phenomenon, and seeing is believing. Well, it isn't really, but it helps, it contributes to believing. So these forms of virtual witnessing, I think, play a really important role in contemporary science.
Okay, so switching gears a bit now to some of the more sociological aspects of science. In your book, Merchants of Doubt, you and Eric Conway argue that groups of people and professional organizations have systematically attempted to misinform the public about science on a host of issues, from the effects of smoking tobacco to acid rain, the ozone hole, and global warming. While much of your focus in this book is on case studies in the US pertaining to public perception and policy, the actions of the US influence activities beyond its borders, including those of Canadian policymakers. How does the campaign of Merchants of Doubt affect the broader international community outside the US?
Mm-hmm. Well, that's a great question, because of course, you know, some people dismissed the book because it was US-centric, and we even at first had a little trouble getting European publishers at first because they thought it was a book about America, and we had to explain, no, this is a book about some things that took place in America, but they're incredibly important for the world because they've had a big impact on the world. So this is actually an extremely important book for people outside the United States to understand what has gone south, so to speak, what has gone wrong. That phrase is kind of prejudicial to people in the South. What has gone wrong in the United States? So, so thank you for that question, because I don't think it's a book just about the United States. But I have to start by just saying, we don't really think of it as case studies. The whole phrase case studies is a little bit of a strange expression to a historian, because they're not cases of some other thing, right? These are not cases of some general principle we're trying to elaborate. This is a history of things that really happened. These are real events by real people who did real things, which in our opinion did real damage. And that's really important to understand, because it's not just kind of a hypothetical argument. This is an argument about what really happened. So what we know really happened is that in 1992, the United States, Canada, and most of the other nations of the world signed the United Nations Framework Convention on Climate Change. That was an international convention, international treaty, to reduce greenhouse gas emissions because of the recognition, even then, back in 1992, so more than 20 years ago, that greenhouse gases and deforestation had the potential to change the climate in damaging and detrimental ways. After the United States signed the Framework Convention, the United States government turned against it and rejected the Kyoto Protocol, which put binding emissions or targets, emissions limit, on the convention. The convention was a statement in principle to take steps to stop dangerous anthropogenic interference in the climate system, and then the Kyoto Protocol to the convention was where the teeth were going to be put into that generalized claim. the United States turned against Kyoto, and that, in a way, effectively derailed the whole process. Because the whole concept of the UN Framework Convention, which a lot of people seem to have either forgotten or maybe they never knew, was that it was a staged approach. That the first step would be the so-called Annex I nations, the United States, Western Europe, Japan, Canada, Australia, the highly industrialized nations. Why? Not just because we were rich and we should pay for it, which is what some people like to say, but because we were the ones who had created the problem. Because if you could have, at that time in 1992, if you could have put a little flag on every molecule of carbon dioxide and methane in the atmosphere, virtually all of those flags would have come from Annex I nations, mostly from the United States, the United Kingdom, and Germany. In fact, those three countries at that time really were responsible for most of the greenhouse gas emissions in the atmosphere. So an interesting historical question is, why don't we just have a treaty from those three countries? But, oh well, different story. So it was completely logical that those nations should have been the ones to first take steps. And the whole idea was that once the Annex I nations did, then the other countries, the developing nations like India, China, and Brazil, who at that time were not responsible for very much emissions at all, but were rapidly gaining steam, literally, that they would be brought on board next. When the United States refused to play ball, that whole thing collapsed, because then China said, well, why should we cut our emissions if the United States won't cut theirs, and the United Kingdom? I mean, for a long time, until pretty recently, the United Kingdom was the #1 nation for historic emissions because they had industrialized so early. It was also the #1 nation per capita for a long time, although that may not be true anymore, I'm not sure. They're still very high per capita, I know that. Okay, so the whole framework gets derailed by the United States refusing to play ball. And then we start blaming China, and we say, but look at Chinese emissions, you know, they're skyrocketing, right? They're like, and it's true, they were skyrocketing, but it was also true that they were skyrocketing, but from a much lower point. So, you know, we're up here, and they're down here. And it is true that eventually China, just recently, China has now caught up. So this is very terrible, because we had 20 years to actually do something about US and European emissions, and that should have been 20 years to then work on getting China on board before it was too late. And now, well, China is still much lower in per capita emissions, a little fact that often gets left out of this discussion, still actually way lower than the United States in per capita emissions, but in terms of total historic emissions, China has not caught up. The other reason why it's of course problematic has to do with Canada. Canada was one of the early signatories to Kyoto. According to Kyoto targets, Canada should have cut its emissions by 6%. Instead, the Canadian government, following the lead of the United States, has now not only rejected the whole UN framework, but withdrawn from Kyoto, and now actually is taking a position of, in fact, denying much of the scientific basis for concern in a really, in my opinion, both intellectually and politically retrograde move. And we know this is highly consequential, partly because Canadian emissions, instead of being cut 6%, they've actually gone up 22%. So this is a huge reversal. And Canada is very important because Canada is pushing ahead now with tar sands and oil, shale, and shale gas. You know, this big resource boom that's taking place in Canada right now, which is actually increasing the availability of fossil fuels, decreasing the price of gas, and actually making it harder for North America and arguably other countries as well to move in the direction of decreased dependence on fossil fuels. So this is a story that has serious ramifications way outside of, you know, the small group of people in Washington, D.C. who we tell the story about.
I see. Earlier this week, the Intergovernmental Panel on Climate Change released the first of 3 volumes of its 5th assessment report. And this work has led to more public discussion about human-induced climate change. What message would you like to leave the public when they're considering the science on climate change and the situation that the world faces right now?
Well, that's a complicated question because it's, you know, such a big issue and there's so many different elements. But I think coming from the perspective I come as someone interested in history and philosophy of science, I think the most important thing for people, for the public to understand, is that climate change is not a problem for the future. Lots of people have the idea that climate change is kind of in the future, and I think that contributes to a feeling that, well, let's wait and see, we don't have to deal with this right now. We could still do shale gas and then we'll figure out the transition to renewables later on. You know, the sort of putting off the reckoning. And that's really problematic because we know the scientific evidence is very robust that the longer we wait, the harder it gets. And many of these changes, like Arctic ice melting, are irreversible. So even if we started working hard next week or next year, we can't undo quite a bit of the changes that have already taken place, sea level rise, things like that. But scientists contribute to this in a way. This brings us back to our topic of modeling, because models are necessarily, well, not necessarily, but climate models are built in a forward direction. They're built in a forward sense. They're built to create scenarios to project in the future what kinds of changes will occur if greenhouse gas emissions continue to rise. And so the language of the IPCC and the language of the modeling community is almost always in the future tense. This will happen if, you know, by 2050, or if CO2 doubles, then, you know, we can expect whatever, blah, blah, blah. And so it contributes to the perception that this is a problem for the future. Now, it is a problem for the future in the sense that it will definitely get worse in the future if we don't do something very, very quickly. I mean, it's going to get worse to some extent no matter what we do, but it will get a lot worse if we don't do something. But actually, climate change is taking place right now. And for that, I think, you know, the media give a tremendous amount of attention to Working Group 1, in part because the IPCC is structured very hierarchically with Working Group 1 at the top, and that's the physical science basis. And then Working Group 2, which is impacts and adaptation, gets much less attention. And Working Group 3 hardly gets any attention at all. But I think, in a way, I mean, if I were head of IPCC, I would, or if anyone asked my opinion, I would suggest that the time has come for Working Group 1 to step back and let Working Group 2 actually take the lead, because now we're really looking seriously at this question of impacts and adaptation. And many of those impacts are already visible now. And the volumes of Working Group 2 speak to that very, very clearly. The impacts on biodiversity, distribution of species, sea level rise, you know, a variety of things, water resource issues, issues on food production. These are all very important issues. People understand that droughts damage crops that cause prices to rise. You know, people get that. People get it that droughts can lead to shortages of water. I mean, these are things we understand pretty well, probably much better than we understand, you know, the thermohaline circulation, right? So it's the impacts piece that I think is really crucial now. And so I'd like to see a lot more conversation about the impacts and a lot less conversation about the details of the climate sensitivity, because I think we're way past that really even being an issue. Look, we know the sensitivity is around 2 or 3 degrees. We know that business as usual is taking us way past doubling, so, and that's 2 to 3 degrees centigrade, so, you know, it's a lot more in Fahrenheit for the US people listening. You know, I mean, some people think that's a problem. Americans hear 2 degrees and they think 2 degrees Fahrenheit, and they think, oh, so instead of it being 70 today, it'll be 72, big deal, right? And of course, the other thing that people don't know about, although this is going to be in my talk this evening, we're talking about the mean global temperature increase. Again, this gets us back to the models. The models are built, designed to try to estimate what the average global temperature increase will be for doubling CO2 or beyond. But that average, in a way, is misleading because many people live in places where the warming will be more than that. And in fact, in many places on the globe, including Canada, the warming is already more than 1 degree. So right now, the globe as a whole, we just heard this week, the total global mean temperature rise is about 0.8 degrees centigrade since the Industrial Revolution. But it's more than that in Canada. It's already above 1 degree centigrade. And so the local impacts on where people live will be different and in many cases greater. And that's pretty serious because if the climate sensitivity is, let's say, 3 degrees, we'll take a slightly upper range of that, 2 to 3, although that's not the worst range that some people think. But let's say it's 3 degrees. But polar amplification makes it, you know, half again as much as that in Canada. Then Canada's not looking at 3 degrees for doubling, it's looking at 4.5 degrees for doubling. And now we go past doubling, now we're not looking at 4.5, we're looking at 5 or 6 or 7. And that's when you start to get into catastrophe scenarios. Because 7 degrees of warming, 7 degrees C of warming is a pretty unhappy prospect.
So do you have any optimism about what solutions there are out there, any projects that give you hope for?
People always ask me this question. It's very interesting to me that I find people find it very, very important that I'm still optimistic despite all this stuff. even though rationally speaking, one has reasonable grounds to actually be rather pessimistic. You know, my meteorologist friends always talk about persistence forecasting, but then I say as a historian, well, it is true that tomorrow is usually like today, but every now and again there's big change in the world, and one of the challenges of history is to kind of understand how do we actually get those big changes. So we obviously need a big change here, but history tells us that big change is possible, so I haven't given up hope. And then, you know, you do what you can do as an individual. So I talk about climate change, and I try to bring this historical perspective that I think is helpful and valuable. And right now I've just signed a contract to put 8 kilowatts of solar panels on my roof.
Wow.
So I'm doing what I can as an individual, and I'm hoping that we'll generate enough electricity that I can also run an electric car off of it, but I won't know until we get it installed how much we're actually going to get. So we'll see if the models, we have a model of how much solar insolation we get in our house, and we'll see if the model proves correct. If the model is right, we'll be running an electric car a year from now. If the model is wrong, then we'll have to do something else, take the train.
Put up a windmill, maybe.
Put up a windmill, right, exactly. Right.
Great.
So.
Okay, well, thank you so much.
Yeah, thank you.